Hello everyone, so today I'm doing a little bit of a session on integration by parts. I will upload other videos regarding different topics that you'll do within the AP exam. I should have sent some sort of a schedule out regarding that. So that being said, here is the video on integration by parts. I can guarantee you that most of this stuff will appear on an FRQ on the AP exam as someone who took it last year. Luckily, you don't have to deal with things like polar coordinates or Lagrange terms, which are probably the most painful parts of the class. So that's fortunate, and you should be able to totally decimate this exam in the best way. So let me get started with two examples. So part A is going to have two examples, and then part B will have another two examples, and those four examples will encompass what I see more or less happening on the AP exam and the sorts of topics that you're going to encounter. So the first thing that I'll go over is just kind of what integration by parts is very quickly. Most of you guys should be familiar with it. If most of you guys are looking at this, you'll see it as a review video. So I'm just going to go in with sine x cosine of x dx. So the main facts when it comes to an integration by parts problem is you'll see two components that can't be mixed in any way, shape, or form whatsoever. So x and cosine of x can't be mixed. I can't turn this into something that can merge with this, at least within my knowledge. There might be some more advanced way of doing it, but that's not what the class is about. So we can't mix these two things at all. So what we're going to do is use integration by parts to take the derivative of one of these and the integral of one of these. So that comes in the form of the integral of u dv is equal to uv minus integral of v du. So you have all these components here, right? So you'll turn your u, which is the thing that you're taking the derivative of, into du, hence the derivative, and dv into the integral, which is v, because you take away the d, which is the derivative part. So that being said, what we'll do is you want to find something that's reducible. So immediately looking at this problem, you see that the x is reducible because x is just going to reduce to an integer or to 0. If I have x squared, that turns into 2x when I take the derivative, and that turns into 2, which then turns into 0. So I can reduce this, as opposed to cosine of x, derivative of that is going to be negative sine of x, derivative of negative sine of x is negative cosine of x, derivative of negative cosine of x is sine of x, and then it goes on and on and on and on and on, and it never ends, right? So you're just going to get more trigonometric problems. So that being said, we're just going to take the integral of this. So our u is equal to x, our du then is derivative of that is just 1 dx by the power rule, and then our dv is equal to cosine of x d of x, sorry for my left hand, and then our integral will just be integral of cosine of x sine of x, and because we're taking the integral, the dx goes away. All right, cool. So now we'll just plug this in uv. So u is x, v is sine of x, minus integral of v, which is sine of x, du, which is just d of x, 1 d of x. Right, and then you could probably solve this integral, add the plus c, or if it's a definite integral, you just solve. So let's go on and talk about the next problem that I want to see, which is integral of ln of x, x d of x. So the first thing that we see here is that x is reducible. But the problem is if we take the derivative of x, we have to take the integral of ln of x. That's just how it works. We split these two up. One is integrated, one is derived. But the problem is that we don't know how to integrate natural log of x. And natural log of x is an exception to this rule where we reduce x. In reality, what we want to do is take the derivative of this because we don't know how to take the integral. Taking the integral of ln of x is not within like the content of the class. We don't know how to do that. So if we don't know how to do it, then we shouldn't do it. We need to take the derivative of this and integrate this, and it'll be okay. So let's do that really quick. Because if we take u equals ln of x, because we're taking the derivative of u, du will equal 1 over x, because the derivative of ln of x per partial fraction decomposition must be 1 over x, because when we do partial fraction decomposition, we know that the integral of 1 over x is ln of x. And you might have just learned this in AP Calc, that derivative of this is just 1 over x dx. And then for dv, we just have x dx, whatever's left over, right? And then our v will just be x squared over 2. The dx goes away, but we have x squared over 2 because we're taking the integral, not the derivative, right? So we have that. So let's just plug this in. And if we plug it in, we go uv, which is ln of x, x squared over 2, minus the integral of v du, which is x squared over 2, 1 over x dx. And we can find here that 1 over x and x squared can combine because x squared is just x times x. So you have an x on the top and an x on the bottom. These cancel out. And so when you get rid of them, you find that you have 1x left over 2 dx. And then you can take the integral of this easily. If I take this 1/2 and move it to the outside, that's just 1/2 integral of x dx. So yeah, that's how you would do this problem, plus c if you don't have a definite integral. If you have an indefinite, plus c, definite integral from the integral from a to b, then you'd obviously have bounds here, and you'd solve for those. So that being said, these are the 2 first examples. We'll talk about the next 2 examples in the next video. All right, goodbye. See you soon.